Hey everyone. The talk should have been about the optimizations in Rust in a Type 4 environment. But preparing those slides, it occurred to me that we'll have to go a little, not a little, quite deep down into why Rust was required in the first place at ZKsync, and we'll have to give you a lot of context. So, what I did was I changed the title of the talk, and this is basically the security issues or the security concerns I have had of Rust, looking at the Rust code in ZKsync. And here's just a short rundown of it. So basically, if any one of you is using Rust in the Web3 industry in any capacity or whatever, this will help you write better code in like half an hour. So strap in. And sorry if you were looking forward to that, we can talk to it after the talk about it after the talk. So yeah. So about me, I'm Rahul Saxena. I work as a security team at ZKsync. Current job, the security job, involves looking at the security of a lot of moving parts in ZKsync, few of which are written in Rust. So that's why you can probably listen to me. And I've previously worked as an independent security and testing consultant for multiple kinds. So I know a bit about security and testing stuff and stuff like that. La 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 la. And if you want to find me on social medias, I usually go by the handle Saxenism, which is written at the last. So yeah, let's go. Oh, okay. Can we run this in Google Slides? Because there was, okay, fine. So this disclaimer is that I'm not a Rust expert. Rust experts exist in the ZKsync team. I just look at their code and find out what can go wrong. So that is my only job. I'm not a Rust expert. And if you were to take my interview for a Rust developer position, I might pass, but I might also fail. So bear that in mind. So, however, if you wrote some non-trivial Rust code and showed it to me, would I be able to find issues in it? Probably yes. Why? Because am I better than you? No, but because that's what I've been trained to do. Like I am not been trained to write good Rust code. I have been trained to find bad Rust code. So I'll just tell you what is bad Rust code and how you can avoid it, and let's go. Okay. So yeah, let's talk about the branding that Rust has. So most of us, at least in the Web3 industry, have been bullied into learning Rust, and we are told that it's very complex, and it's also somewhat very safe. So people assume that if you can write Rust, that is proof that you are like a giga brain and your code will not have mistakes. So basically that's the branding around Rust, and that's why every second person you see on Twitter and on real life just says that, hey, I'm working on learning Rust. Why? No clue, but just learning Rust. Anyway, so broadly speaking, that is true. Like it is a safe language and it does make you look like a genius, but there is a lot of context that is missing. What is the context? In my experience, limited experience, Rust as a language is not very difficult to grasp and write. Like to understand what Rust is trying to do and to write in Rust is not very difficult. However, it is extremely opinionated. Rust wants you to do things in a Rusty way, and the difficulty that comes up is when you do not try to understand that Rust way and try to write your things your own way. For example, the biggest issues I've seen is that people who have experience writing C and C++ code, they come to write Rust code, they face a lot of issues, not the Rust beginners, because Rust was basically made as an antidote to all the issues that came up in C, all the memory issues. So Rust wants you to do things in a certain way, and if you do not do it, that increases the complexity and difficulty, not the actual difficulty of the language. And of course, if you come from a background with zero memory management, like if you have just written Python, JavaScript throughout your life, not even JavaScript, like Python throughout your life, and you say that, hey, I'm going to learn Rust, it's going to be difficult for you, just a little. But I think that's not a problem for anyone here, so yeah. Yeah. So let's now talk about the safe part of the language. Like people say that Rust is a very safe language, and I've seen that it gives people a very false sense of comfort, in the sense that it is memory safe. For example, when people write C code, it was very fast, but it was also very dangerous because everything you had to do with memory had to be manually done. Rust, after that, a lot of languages came, Java, Python, whatever, and they managed memory for you, abstracting away all the memory management, but they were not performant. So Rust came along with a borrow checker model to do a lot of compile time checks and make sure that your memory management is being done right. And that compilation time takes time, but the runtime, again, is just as fast as C or any other low-level languages. So that's what the safe part of Rust is. But if you, but if you're writing software for a missile or a submarine and you do not want your 4.9999995 to be rounded to 5, that is something that you'll have to deal with yourself. That is not the kind of safety or security that Rust provides. So you have to have a very clear delimitation in your mind, like what does safe even mean? Like safety here is just about memory, and that also is not perfect because we have unsafe that we'll talk about later, and unsafe does not mean unsafe. Unsafe just means that there are a few things that you need to do in memory that cannot be modeled in the borrow checker or cannot be modeled formally at compile time. You have to do unsafe things to make it work. So yeah, that's the safety guarantees of Rust, not the safety guarantees that you want in your own context. For example, if you're running a lending protocol and if you want your shares to basically map to the amount of money you should have, it should be rounding in the perfect direction, and it should be calculating based on the perfect decimals, not rounded in the round direction. That is the kind of security you'll have to do on your own. Cool. So yeah, common Rust bugs. What are the most common, easily avoidable issues that crop up when devs write Rust? Okay. So this is going to be a short and a fast list. If anyone has any doubts, just let me know. So, okay, so if you can read this code, can you tell me if this would compile or not? So I'll tell you what the caveat is. Like I've defined two types, meter and feet of F64. And the deploy emergency landing gear takes height in meters. But in main, I've called height with feet. So does this thing compile or not? Yes? Does this thing compile? No? Who says no? Who says yes? Show me hands. It shouldn't, right? Okay. Does it? yeah. That's a good caveat. It shouldn't, but does it? Yeah. So yes, it does, and that's the sad part. So this is actually a pretty good example. I mean, I wrote it, so it's good. So if you had written a software for landing an aeroplane, and one of the function was, should we deploy emergency landing gear, which should be activated at a certain altitude, and that altitude being expected is in meters, and 10,000 meters is equivalent to 33,000 feet. So basically, if you say that the height is less than 10,000 meters, deploy the emergency landing gear. But if you're supplying the height in feet, and in feet the height is 20,000, so 20,000 according to this program is still a lot above 10,000, but 20,000 feet is like very less than 10,000 meters. So the landing gear should have deployed, but in this context it won't, and people will die, as has happened in Boeing before, but that was not the case, it was something else. So this is a very common type of bug. This is called type aliasing. I think everyone knows that. And the issue here is that this sort of thinking, like to do stuff, comes from traditional languages, Python, JavaScript, stuff like that. And this is not the Rust way of doing things. And that's why you are in a bad position right now. So yeah, the Rust way of doing things is declaring structs, feet and meter, and then providing the implementation for feet, like the traits. So basically, you're telling Rust compiler that, hey, there's a certain type of thing called feet struct, And that feed struct should be able to convert things to meters with this particular function. And when you use those particular things, then this kind of mistake won't happen. If you provide the height in a feet struct and it was expected to be in the meter struct, it won't compile. So if you're defining a new type anywhere, it's almost always a good idea to define how you want it to behave, and that's where traits come in. So traits is basically what the struct does. So it's defining what the struct is like. Any problems so far? No? Cool. Okay, not removing uncertainty from your code early. So this is basically not a bug per se, but something that I've seen causes a lot of headache later on. Because this kind of things do not get caught at the very beginning. They get caught when they have fucked up at least 25 different things, and you have to figure out individually like what actually went wrong. So what you can see here is that the example that I'm taking is that you are dealing with the string, and you're parsing that string, and from that string, you're assuming that the name of this particular person is Alice, and her age is 30, right? So if you take an example of this, like this JSON string, this is hard-coded, so it won't go bad. But if this input is, you're getting it from a HTTP request or some user input, it is quite possible that this information is malformed, and the parsing that you do, it won't be correct. And the issue with that parsing is that most of the time it does not throw up any error until you specifically mention that, hey, you should throw an error. So what happens is that what I typically suggest is that if, so instead of doing string parsing and stuff like that, just convert what you want into a type of struct that you want. So basically, if you want that string to become a type of struct, which is the person result, so just create structs for it with the traits name and age, and basically parse everything into it so that it becomes more solidified. Like you can just do this person dot name and see if there is a valid value or not. Like it should return some result, and if it is okay, so then it's fine, but if it's null, it's not fine. So yeah, don't leave stuff hanging out on like chances, create solid structs. Yeah. So this is something that I've noticed on the mental side of things for the developers. Like they really hate putting in asserts in the statement, in their at least release code. Like they can use debug assert for the time I've seen, but they do not like putting asserts because assert is quite a hard stop. And if you put it, it like jams the program, it stops everything. So when you have a serious enough issue, which if true, it would be better to completely stop the program and fix the issue rather than try and continue running the program, which is like you handle the error and you do something, and keep the program running. Instead of that instinct, if you think that a very important invariant is getting broken, it's better, in my opinion at least, to use an assert statement and cut the program short. Like this seems like an obvious point, but you'd be surprised how many people are just subconsciously not willing to do it. And this is also a great cue to incorporate the fry-pie pattern into your Rust code. Like anyone knows what the fry-pie pattern is? It's from the solidity realm of things. So okay, if you don't know it. So fry-pie pattern basically means that whenever you're writing a function, has anyone heard of the CEI pattern in Solidity? Checks, effects, okay, nice. So the check effects interaction pattern, if you'd like to tell us what it is.
Yeah, it's a way to ensure that first.
Yeah, anyone, yeah. Like, you got it, yeah.
So it's a way to ensure that first the effects are done and then external calls by the end, basically.
Okay, yeah. So it was basically introduced as a measure against reentrancy. So what it said that, hey, first you do all the checks that are relevant in a function, and then you do all the effects on the smart contract that it should have, like all the state changes, and only then do you interact with the external third party that is supposed to be interacting with the contract, okay? Because if you're interacting with the third party early on, it is possible that they re-enter your contract and exploit your contract. So similar to that, we have the fry pie pattern, which says that first of all, we check function requirements, which is the checks, then effects, and then interaction. And then after that, after running that function, we also check for the protocol invariants. For example, if you are using a lending protocol and someone deposited their collateral, so you do all the checks like, hey, was the collateral on time, and was the collateral exactly the amount that we wanted, stuff like that. But there is also a protocol invariant. It could be anything like, for example, that the total amount of collateral in the system theoretically should not be lower than the amount that is lent out. So yeah, it is the protocol level invariant, like the entire system invariant. And if you understand using asserts and you run a particularly risky function, you can write an assert for the entire program. Like in the entirety of the program, for example, the compute cycle should not exceed this maximum limit after running this function. So that is the fry pie pattern which Nascent came up with. So yeah, hat tip to them. In this point, does anyone have any issues, qualms? No? Cool. Okay, so I think, yeah, this is a universally told thing. Everyone gets told that, hey, whenever you have errors, handle them gracefully, don't just let them panic, stuff like that. I don't think I need to tell you anything here. Yeah, so in case of unrecoverable bugs, so basically bugs that are not part of the result and options error thing, which directly lead to panic. I've seen many a times people go into their config.toml file and put panic equals to abort. So what that does is that whenever there's a undefined, unhandled panic in your code base, that aborts the entire program and the program just quits. It does not make sense to do it, but people do it because if you Google Rust optimizations, it's one of the top things that come up that, hey, put panic is equal to abort, and that will reduce the binary size. So either you are super confident that nothing in your program can unexpectedly panic, then do it, otherwise don't. Like, it does not have much upside. So panic, basically, whenever there is a panic that is not expected in your program, you can program it to run, you can program it to be running according to two ways. One is unwinding, and the second is abort. I just told you about abort. I don't like it. Doesn't make sense. The other thing you can do is unwind. So that basically stops the particular thread where the panic happened, and you can kind of do some kind of error handling on top of it by catching that particular unwind and putting out some custom message so that the user knows something happened with the message, and you also can figure out where things went wrong because of the message. So, right, and why this is good in the sense that if you're setting panic to unwind is that, like, let's take an example of ZKsync. ZKsync has multiple components such that it has L1 smart contracts, L2 smart contracts, system smart contracts, bootloader, circuits, out of circuit VM implementation in Rust, stuff like that. So if a particular component is facing an attack, like the Rust system is facing an attack somehow, like some adversary is being able to put in some inputs that is able to DOS the system, and it is making the entire Rust program panic. And we want to know the values, like what is that is being passed that is making the system panic. We can use panic is equals to unwind and specifically propagate the values that came to us, because in unwind the program doesn't stop. You can actually push the program beyond the panic by catching it, and in the catch you can just put in the input values that are offending your system. Okay. Again, unwrap and expect. So unwrap, it's good for POCs, like if you want to write code fast, if you want to just have a proof of concept, it's fine. The issue with that is at least in Web3 companies, what I've seen, like it's sort of human element. I'll talk about it. So usually a protocol starts with a 10x dev, and he or she or they hire a couple of other 10x dev, and all they care about is getting the things to work. And they start with the POC, and they just keep on building on top of it. And what I have seen is that once Unwrap gets into a sufficiently non-trivial complex code base, it's almost impossible to remove it, because then there are so many things that you have to match the errors to, that people just cannot understand like how are things coming and how are things going. Like it's not that you cannot do it, it's just that whoever is reviewing the PR will have a very hard time understanding how are all these errors coming up. So it's hard to remove it. Like I've seen very less instances of Unwrap getting removed from complex code bases. So do not do it. Handle errors well, and at the very least, go for expect. Like for the places that you are very sure that error will never come up, just go for expect, so that you can leave a custom string, and you at least know where the error is, right? The only difference between unwrap and expect, at least in what I know, is that expect is the same as unwrap, but you can also provide a custom error string. Everything cool till now? Okay. So yeah, this is one of the biggies. Integer overflow and underflow. So what happens is that, at least in the debug, profile.debug Rust code basis, if an integer is overflowing or underflowing, it leaves a protocol, it leaves a compiler warning, it leaves a compiler error that, hey, this particular thing is overflowing. But in release mode, these underflows and overflows are silenced. So what happened is that if you're doing some sort of typecasting, like if you have a large integer like 4,000 and you typecast it to u of 8, then it won't give out an error, it will just silently underflow in the release mode. So to handle that, to gracefully handle that, we use something called the checked maths, and the checked maths is basically checked add, checked div, etc. And there you basically, does anyone know what checked add and checked division and checked? Yeah, sure. What is it? What is it? Mm-hmm. Yes. So the addition, like if you do an addition of two U8 maxes and you expect a U8, it will give you an error that, hey, this is overflowing. So this is how you handle errors in addition, multiplication, stuff like that. And sometimes also what happens is that if you can also use saturating maths, in the sense that if you add, for example, U8 max and U8 max again, and you expect a U8, then what you will get is the maximum of U8. So whatever happens, you either get the maximum value as the maximum of that particular type, or the minimum of that particular type. So based on your particular scenario, like for example, whatever DeFi protocol you are using, whatever infrastructure code you're writing, it might be feasible that you use saturating maths. And what I would say is that you have to be really careful with saturating maths, because there have been a couple of hacks in the near ecosystem, where people use saturating maths because that is what makes sense, because you do not want the numbers to exceed a certain limit, but they miss out a few edge cases, corner cases, and bad things happen. Okay. So let's see this example. You have a U32 as U32 max and another U32 as 1. If you add it simply, it would result in an overflow, and you will get, again, 0 or 1, I guess, 0. And if you do a checked addition, then you will get this thing, this none. And again, if you do a checked division, you'll again get a result if it is underflowing. This is saturating add. So for example, if you add U32 max with 1 and you have a saturating result, so what you'll get is that A saturating add B is the maximum of U32. Okay. think I have a couple more things, but we do not have the time. Okay, let's discuss the last thing. Rest of the things we can discuss later. So I'm really interested in what do you guys think of when we say unsafe Rust? Like, what comes to your mind? Yeah.
Like, oh, you're gonna like drop down into like a place where you
Mm-hmm.
need, maybe to work at like write assembly. So I kind of like,
Yeah.
sometimes I look at it as like, oh, this is a necessary evil for this
Yeah.
sort of thing.
That's nice. That's nice.
You reference null pointer.
Yeah. Yeah. Okay. That is definitely one use case why people use it. But like, what comes to mind? Like, whenever I've talked to people who are not very proficient in Rust, like who haven't written anything non-trivial, they avoid it like the plague. That hey, we should not write anything unsafe. Why? Why is that the case? Like, is it even true?
We go back to C.
Yeah.
We go back to C.
Yeah. Yes.
The guarantees of the Rust runtime are very hard to uphold if
Mhm.
you don't understand the runtime very well. At least at the beginning.
Yeah, that's right. And that's exactly right. Uh, for me, it's actually just not a good name. Unsafe Rust just says that whatever you're writing is unsafe, which is not true. I would say that the better name could have been not Rust code or whatever, because
Not provable.
not.
Not provable.
Yeah, right. Yeah, right. Because like at the end of the day, you are dealing with the computer, and as much as you want to pretend, there are no inputs outputs. There are, and sometimes you have to deal with raw pointers, mutable global variables, and whatnot. So basically, things that Rust tries to provide from architectural standpoint, but you have to do it because the program demands it. And one of the biggest reason people typically use it to interface with C code, and when you interface with C code, you have to deal with null pointers, raw pointers, not null. So yeah, you have to use unsafe here and there. So with the keyword unsafe, what you're actually doing is in fact telling the compiler that, hey, this piece of code that I'm writing is safe. I can't prove it to you, but it is. Like the code block should have been called trust me bro, but like I think that that's the real name. But this is the important thing. Like whenever you write unsafe code, you are telling the compiler that, hey, I truly believe that it is safe, but I cannot prove it to you, so just let me run this, okay? And the very big caveat here is don't break the compiler's trust. Like in life, don't break anyone's trust. Here, the compiler is trusting you that, hey, I'm letting you write your own spaghetti code, but don't do bad stuff. Like now you can access, like multiple people can access the same memory, you can use memory after it's destroyed, stuff like that. Don't do bad things. So think of it like when Rust was designed, it baked into its design and rules that prevented a lot of memory-related mistakes that people made when writing C code. I think we already talked about it. Yes, but not all the memory usage cases can be modeled into perfect Rust, and that too at compile time. So at these times, you have to step up, and then you take the responsibility from the compiler to ensure that your program is in fact safe. And of course, this is all assuming that you are a good developer and not abusing unsafe to do things for which Rust already has a way to do things. These are the guidelines, and yeah, I think we can provide the slides later. Okay, thank you. And does anyone have any questions or?